Hello and welcome to another power system analysis class. In the previous class, we finished the transformers, three-phase transformers, and the modeling of three-phase transformers. We solved some problems today, and we also spoke about different type of transformers, such as auto transformers and so on. And the last part we discussed was auto transformers. They are magnetically and electrically coupled. They are usually used for low voltage. You can't usually use it for when you want to step down a very high voltage because it's electrically and magnetically coupled. Sometimes it may be dangerous. And these type of transformers, as mentioned, are modeled as a regular transformer in power flow as well. Today, we're going to start with models, flow, and the bus admittance matrix. The reason that we need to study flow and model is because the grid is like a live animal, I could say. It's not as static, it's dynamic, and you have ups and downs. This is an example of a solar farm output. And as you know, in a solar farm, even during the day, during night, you don't produce anything, obviously, but during the day, even you have clouds coming in and out, you have rainy days, and you have fluctuation in power production. And you have to take that into account. Also, we have fluctuations in the load as well. We have peak hours, off-peak hours. Some seasons we have higher demand, some seasons we have lower demands. So we have to take all of these into account. Now, the way that we can model this system are different ways that we can model this, and we can find the power flow. Power flow obviously means the flow or direction of the power and the amount of power that it's moving through the transmission system. Now, the ultimate goal is to supply load with electricity at constant frequency and voltage. We don't want the frequency or the voltage to fall. If you add a huge load to the system, suddenly you're going to have a drop in the voltage and frequency sometimes, and that sometimes could be dangerous for the system and for the load, for the generation, transmission, and so on. And the other thing is that electrical characteristics of individual loads matter, but usually they can only be estimated. We don't have perfect models. All of them are estimations, and I'll explain more about that. In real world, loads are constantly changing, and loads are consisting of large number of individual devices. We don't have a single load. Usually we don't have a single big motor. Like a household, you have a dryer, washer, if you have electric stove, your TV, and you don't turn them on all at the same time. Your lights, you may turn them on at night. You don't turn them in during the day. So it's not like a single device that you switch and turn it on and you would know, and you can model how much power you're going to get and switch it off. That's the reason modeling is going to be very difficult. And the other thing is only limited network observability of load characteristics. Average models are typically used for analysis. We have two common types of models. We have the constant power, which we model the power SI, obviously, as you know, is PI plus JQI, real power and the react power. And the other type of model that we have is usually the constant impedance. And as you know, the equation for impedance to apparent power SI is going to be V squared over ZI. Now, these are very interesting scientific modeling quotes that I've added here. All models are wrong, but some are useful. This is from George Box, Empirical Model Building and Response Surfaces. Box went on to say that the practical question is how wrong they have to be not to be useful. So we don't have a perfect model at all. we can have a good estimate that could be close, as close as possible. Very similar to, weather prediction models. You won't get it right, but you can predict you're going to have a, cloudy day, but you don't know for sure if it's going to rain for certain, or and that's the reason they put a, probability in percentage. They say 60%, 40%. And do you know what the 40% means? So some people think that 40% means there's a 40% of chance of rain. Actually, 40% means that in that specific area, like say Amarillo, it will rain, but it will only rain in 40% of the area. And we don't know where area. So there is a cloud passing. We don't know if it's going to fall in Canyon or Amarillo. We know it's going to rain, and it's going to rain in 40% of that area. If it's 100%, means that it's going to rain all over Amarillo. If it's 10%, it's going to rain 10%. But we don't know where this 10% is going to fall. So this is how they model weather. And by the way, we can't model more than 7 or 10 days. We have annual modeling, but they are very, very random. So everything should be made as simple as possible, but not simpler. That's fine, Einstein. And then with 4 parameters, I can fit an elephant. And with 5, I can make him wiggle his trunk. And this is from John von Neumann. So as mentioned, models are very good estimates. They are not perfect. We have different types of systems as well that I would mention, nonlinear and linear models. First thing that you need to know for generator models, engineering models depend upon application. Generators are usually synchronous machines. We also have asynchronous generators as well, mainly used in wind turbines. But I would say 95% of our generation system, even more, are synchronous machines. By the way, in solar panels as well, we usually convert them to AC, and we have an inverter that is, gets a feedback from the grid, and it synchronizes the frequency and also the angle very, very precisely. It's even faster and more accurate sometimes than a mechanical system. So in a generator, what they do usually is the frequency is determined by the RPM of the generator, and it depends on the number of poles. It's 120 F over P, the equation. So when the frequency drops, they have these. If it's a gas turbine, for example, they'll open the valve a little bit, so the rotational speed of the rotor goes higher, spins faster, and creates a higher frequency. And that usually takes a fraction of sometimes it's a few seconds. But in a solar system, because it's all electrical, that's the mechanical part that you have to open the valve, wait until it increases, so on. But in an inverter, because everything is electronically controlled, it's done in a fraction of a second. And also you can perfectly match the phase as well. For a generator to match the phase, usually sometimes it takes like half an hour or an hour to match that. So what they would do is, and I would draw this here, for a generator, and we call what we call a synchronometer. It actually synchronizes the generator with the grid. So imagine if the grid signal or frequency looks like this, and my generator looks like this. So the blue one is the generator, the black one is the grid. Now, both of them have the same frequency, but there's a phase shift. So if I connect this generator to this grid, what happens? Cause a huge damage. Sometimes even the frequency shift is 90 degrees. So when that is positive, the other one is negative. So you're going to have huge problem. So what they do, it's a synchronometer. I don't know if you see it. It has something, it's like a clock, and it shows the difference in the angle. So do you know how do we synchronize the generator with the grid? How can we do that?
Speed the generator up
Yes, perfect. We can speed up the generator. Actually, we alter the frequency, and what we do, for example, we would speed it up or speed it down until we can match this. Okay, so what we do is we speed up or we speed down. Sometimes we can speed up or speed down until we can match this. And this actually, it's not an easy task. It takes a lot of feedback and back and forth. And sometimes it takes 20, 30 minutes, an hour. That's the reason when a generator is, is disconnected from the grid, it's not as easy as flipping a switch and turning on the generator, connecting to the grid. Synchronizing the generator with the grid is a difficult task. First thing, the voltage must match. You can't have a mismatch. If the voltage is lower than the grid or the frequency is lower, the generator would actually act like a motor and it will act like a load. So the voltage should be a little bit higher than the grid. That's the first thing. Secondly, frequency must match. If you have a mismatch in the frequency between the grid and the generator, again, you're going to have huge problems. And the third thing, you must match the phase angle. And the way that we match the phase angle is by playing with the frequency of the generator that we have control of, and then be able to match that. So that's the reason you shut off a power plant. First of all, the mechanical part to heat up the boiler, it takes like maybe 5-6 hours to reach a specific temperature if you're using, let's say, a coal power plant or even a gas power plant. And then you have to match the voltage and the frequency and the angle. So it's not like a simple switch of a, flip of a switch. Sometimes it takes 12 hours. For a nuclear power plant, it takes much more, or sometimes 24 hours, even more than that. So that's the reason matching that and putting schedule, maintenance is a very difficult task. Yes.
Once you have your generator locked in with the grid frequency,
yes.
Does it naturally want to stay there, or do you have
to? Yeah, do you have to constantly be? So the thing is, a good thing about the grid is the grid itself acts a little bit, has a little bit of cushion. It acts like it stores a little bit of energy in the system. So it's not like if you flip a switch now in your house, the generator would run a little bit higher. It could absorb a little bit of load and, but if it's a huge load, let's say you have a steel factory and you have these huge furnaces and all of them mostly work on electrical. It's not like they can easily turn that on. It's going to have effect on the generator, so you have to be able to match that. Usually what happens is the frequency and the voltage drops a little bit, dips, and then the generator picks up that. It takes like a few seconds. But that's like as mentioned, it's like a creature that it's alive. It's like a dynamic thing that you have to constantly manage. Yes. But it does it to a very certain degree. If you measure the frequency of the grid right now, if I had an oscilloscope, I would show you. It's not exactly like 60 hertz. It's like 59.8 to 60.2 if you want to measure it very accurately sometimes. So there is a little bit of cushion. And the voltage as well. It's not exactly 120. Sometimes it's going to be a little lower, higher. But that's acceptable, And that's the reason we have the system. Sometimes you may see it during the summer. This is a good example. Have you ever had the experience of turning on your microwave in the morning and at night, and you see at morning your food will warm in a minute, at night it takes 1.5 minutes, and you would see that the lights would dim a little bit. That's the reason you don't have enough, power. All that neighborhood is consuming a lot of power, so you don't have that much current to get from the grid, so you're gonna have a lower power coming in. But again, that's gonna be a little bit, it's gonna be okay, and it's gonna work. Now for wind turbines, asynchronous motors are used most of the time. Now we have permanent magnet wind turbines as well. The reason that we use asynchronous, and it's very difficult to get a synchronous, because wind speed changes constantly. If you have a thermal power plant, like a gas power plant, you have a valve that enters the steam or the gas into the turbine, and you can easily control that. With wind turbine, you can't control the wind speed. Therefore, the motor may spin 10 RPM, and next minute it would do 15, and then 5, and then 20, and then 30. So it's constantly changing. And if you had a synchronous motor, the frequency would constantly change with the RPM. As mentioned, as you know, RPM is equal to 120 F over P. P number of poles. Usually there are 4 or 2 poles, depending, or sometimes 6 poles, depending on the generator. So what you're going to get is a output that is constantly changing the frequency, and we don't want to do that. That's the reason we use asynchronous. And the other thing is, the actually better approach sometimes is just to convert it to DC and have an inverter convert it back to AC, because it's much easier to control that way. Now, for generators, we will use 2 different models. We use the short-term model and the steady-state model, which is, I could say, technically the long-term model. A steady-state model, treating the generator as a constant power source operating at a fixed voltage. This model will be used for power flow and economic analysis, again, if we want to do a little bit long-term. And then we have a short-term model, treating the generator as a constant voltage source behind a possibly time-varying reactance. And this is an example of how we model it. Now, an important thing in modeling these systems is power flow analysis. Now we have the necessary models to start to develop the power system analysis tool. The most common power system analysis tool is the power flow, also known sometimes as the load flow as well. So power flow determines how the power flow flows in a network. It's also used to determine all bus voltages and all currents, and I'll explain that. I will solve some problems with that. Power flow is a nonlinear analysis technique because of a constant power model. I would explain different systems that we have: nonlinear, linear, and which systems are in the linear category and which systems are in the nonlinear category. And the last thing is that the power flow is a steady state analysis tool. So if in the exam we ask power flow, if it's a short term or a steady state, it's a steady state analysis tool. Now, a little bit explain, you already know about linear and nonlinear, difference between them. We have linear and nonlinear systems. Linear systems, in a linear system, the output is proportional to the input, and the principle of superposition holds. This is an example, like y is hx, the function, and which could be cx, and y would be cx1 plus x2, which is equal to cx1 plus cx2. Very simple. Nonlinear example, y is equal to hx or cx square, and y would be cx1 plus x2 square, which is not equal to cx1 square plus cx2 square. It doesn't hold the superposition principle, and the output is not proportional to the input. Can you give me an example of a nonlinear element in electrical engineering, and a linear? Power, you can say constant power, yes, is nonlinear. Different elements that are linear are like resistance. R is V over I, it's a linear. And independent voltage and current source are also linear. Now, for some examples, inductors, capacitors, independent voltage source and current sources are all linear circuits. Why? V is equal to Ri. R would be V over I, so it's a linear equation. Also, impedance for a capacitance is 1 over j omega c, and for inductance is 1 over j omega L, or j omega L, I'm sorry. And all of these are linear systems. And such systems may be analyzed by superposition. Can you give me an example of a nonlinear element?
Regulator feedback.
Yes, that's a great. Another very simple one is a diode. A diode is a nonlinear system. This is a graph for a diode. For a resistor, the graph looks like this. Yes, diode is completely nonlinear. You can, if I have an ideal diode, you can say in this little part it's linear, but the other parts, you have a nonlinear side. So diode is an example of nonlinear elements. Another example is a constant power loads and generator injections. These are nonlinear, and hence systems with these elements cannot be analyzed by superposition. These problems sometimes can be very difficult to solve and usually require an interactive approach. That's the reason modeling is it's going to be very difficult. Sometimes what we do to make it easier, like the example that I showed you with the diode, is to just find it in a very small time frame and assume that it's linear. But it doesn't work always. It sometimes works in communication systems that say, okay, in the diode, in the reverse bias for a linear diode, we would assume that it's linear in that little part. But it doesn't always work. Now, the problem with nonlinear equations is sometimes they don't have any answer at all. Sometimes you may have multiple answers for a same question. This is an example. Example number 1, x squared minus 2 is equal to 0. It has multiple solutions. Solutions could be positive or negative 1.414, which is the left graph. You can see you have at least two. Sometimes you have multiple solutions. Sometimes you have close to infinite. Now, example number 2, x squared plus 2 is equal to 0. This one has no solution. So in a nonlinear, you may have multiple solutions, or sometimes you won't have any solutions at all. This is an example of a multiple solution example. The DC system shown below has 2 solutions, where the 18-watt load is a resistive load. The equivalent we are solving, I square R load, is going to be V square over R times R, which gives us 18 watts. So one solution R is 2 ohms. The other solution R load is 0.5 ohms. Now, what is the maximum load? The maximum load is when you have P load, when you have the minimal R load. So when you put 0.5, you can get the maximum load here as well. Or I'm sorry, the maximum R load that you're going to have. You're going to have a maximum P load, which is 2. You can put 2. Now, it's a general way to solve power flow problems is to use the bus admittance matrix. For those who had smart grids, you maybe with me already familiar with this, but one of the standard models that we use to solve power flow in the power system is using the admittance. Do you remember what admittance is? What is Y? Z. 1 over Z. So admittance is the opposite of impedance. Admittance actually gives us conductivity. So the lower the admittance is, it means you have higher resistance, and the higher the admittance is, you have lower resistance, meaning the higher the admittance is, you have better conductivity. So copper has a higher admittance than aluminum, for example. Now, according to Ohm's law, do you remember what Ohm's law is? V is equal to what? IR or IZ impedance, yes? So if I replace impedance with 1 over Y, then V is equal to I over Y. Am I correct? In other words, it would be equal to YV. Now, I can write this as a matrix and solve for the voltage and the current by just knowing the current and the admittance, or the voltage and the admittance. Now, first step in solving the power flow is to create what is known as the bus admittance matrix, often called the Y bus. The Y bus gives the relationship between all the bus current injections I and all the bus voltages V. I is equal to Y bus V. Now the Y bus is developed by applying KCL at each bus in the system to relate the bus current injections, the bus voltages, and the branch impedance and admittance. Now, it's the best way to learn this is via an example. Now, we have a network here, and we want to determine the bus admittance matrix, assuming the current injection at each bus is II is equal to IGI minus IDI. Now, the round one is the generator, and the arrow shows the load. The generator current is IG, the load current is ID. So at this node, let's say I1, you're going to have IG, the generation, minus the load that you have. Now, and we don't know if this is actually getting power or giving power, and I'll explain. Depending on the direction of the current and if it's positive or negative, we can determine if this bus is actually receiving power for the other buses or it's delivering power to the other buses. Now, by KCL at bus 1, if I want to do it as bus 1, this bus over here, I1 would be equal to IG1 minus ID1. So this is G1 and this is D1. Now I can write it like this as well. I1 would be equal to I12 plus I13. The current that is between bus number 1 and 2 and the current that is between bus number 1 and 3. So the current between the bus number 1 and 2 is the voltage between 2 and 1, V2, V1, over its impedance ZA. So I12 would be equal to V1 minus V2 over ZA, and I13 would be V1 minus V3 over ZB. So I can write this equation like this. I1 would be I12 plus I13, and it's going to be V1 minus V2 over ZA plus V1 minus V3 over ZB. I can replace ZA with YA because ZA is equal to 1 over YA and ZB is 1 over YB. Now with YJ equal to 1 over ZJ, we can simplify the equation. YA plus YB times V1 minus YA V2 minus YB V2. Similarly, we can do it for I2 and I3 and I4, all the buses. So for I2, it's going to be I21 plus I23 plus I24. And it's going to be negative YA V1 plus YA YC plus YC plus YD V2 minus YC V3 minus YD V4. And if I write it for the entire network, we have 4 currents, I1, I2, I3, R4. Depending on the number of buses that we have the same number of currents. How many buses that we had, nodes that did we have? We had 4, so we have I1 to I4, and I would be Y bus over B, and Y, the first one would be YA plus YB minus YA minus YB and 0, and on the right, you're going to have V1, V2, V3, and V4. So for a system bus with n buses, Y bus is an n by n symmetric matrix, meaning Aij is equal to AJI. So if I have 4, you're going to have a 4 by 4 matrix. Now the diagonal ones are the self-impedance, meaning the impedances that are just going into that bus, and the non-diagonals are the admittances between those two. So for example, for between bus 1 and 2, what is the impedance between bus 1 and 2? Yes, so the impedance Z12 is equal to 1 over Y12 or in other words, y12 is equal to 1 over z12, which is equal to 1 over what? ZA. And 1 over ZA is equal to what? YA. Okay? So the same thing for between 1 and 3 is going to be ZB3, between 2 and 3 is going to be ZC, and between 2 and 4 is going to be ZB. So as you can see, and the diagonal one is the self-impedance that we have. So which impedances are connected in total with bus A? It's going to be ZA and ZB, which is YA and YB. So for the first one, it's going to be YA and YB. What about the second bus? Which impedances are connected to the second bus? The second bus, this is bus number 2. Or which admittances are connected to second bus? ADC. Why ADC? Y of A plus Y of D plus Y of C. Perfect. And what about bus number 3? BC. Yes, it's going to be YB plus YC. And what about bus number 4? D. So it's going to be only D. So the diagonal ones are all the admittances that are connected to that node or bus. Now the off-diagonal ones, as mentioned, so for example, between 3 and 2, what is between 3 and 2? What impedance do we have between 3 and 2? C. So it's going to be negative YC. Okay. So Y bus general form, the diagonal terms Yij are the self-admittance terms equal to the sum of admittances of all devices incident to bus I. The off-diagonal terms Yij are equal to the negative of the sum of the admittances joining the two bus. So the admittance shared between two of the bus is going to be negative of that. With large system Y bus is a sparse matrix. That is most entries are 0 for that. So you're going to have a diagonal one with the result being 0. In Schon's terms, such as with the pi-line model, only affect the diagonal terms. Now, let's solve a problem. We have a 3-bus system. I want you to solve this. And Z12 is 0.2, Z13 is 0.25, and Z23 is 0.5. We want to find Y bus. So we have 3 bus, Z12 is 0.2, Z13 is 0.25, and Z23 is 0.5. So this is 0.2J, 0.25J, and 0.5J. This is bus number 1, 2, and 3. I'll give you 5 minutes to solve this. Do you want me to go back to the equation? Yes? Okay. The matrix that you had. The first student to solve this gets extra points on their next exam. By the way, the upcoming exam, I will send an announcement for the upcoming second exam. It's going to be probably maybe next week. Yes, to the question. Okay. So this is the question. You have 3 nodes or 3 buses. Therefore, you're going to have I1, I2, and I3. You're going to have a 3 by 3 matrix and V1, V2, V3. Did anyone solve it? Has anyone solved it? Okay. Let me solve this one. I think the next one would be easier for you. So first thing, we have the impedance. We need to find the admittances. So y12 is equal to 1 over z12, which would be 1 over j.2. So what is 1 over j.2? Yes. Negative j5, actually. Yes. 1 over j is negative j. And the same thing for y13. It's going to be 1 over j.25, which gives us negative j4. And y23 is going to be 1 over j.5, which gives us negative j2. So I have the admittances. Now I need to find the diagonal terms. So the diagonal terms, I need to find y11. Now y11 is going to be the impedances to node number 1. It's going to be the summation of the admittances that we have, which is going to be y12 plus y13, which is going to be negative j5, negative j, which is negative j9, I think. Okay. Now y22 the same way is going to be y12 plus y23, which is going to be negative j5, negative j2, which is equal to negative j7. And finally, y33 is going to be the same 3. It's going to be y13 plus y23, which is negative j4, negative j2, which is equal to negative j6. So now that I have all the ones, the admittances, I want to find the off-diagonal terms. So I'm going to find the off-diagonal terms. So for that, y12 would be equal to y21, which is equal to negative j5, because it's going to be the negative of that term, gives us j5. And same thing, y13 is equal to y31, which is going to be j4. And the same thing, y23 is going to be equal to y32, which is going to be equal to j2. Now the bus admittance would look like this. You're going to have y11, which is negative j9, then y12, which is j5, then y13, which is j4. And then you're going to have, again, here j5, and negative j7, and j2, and then j4, and then j2, and negative j6. So as you can see here, in an admittance matrix, these are the self-admittances, and these are exactly copied. So this, and this, it's copied. So if you find the upper half, the lower half, because y12 is equal to y21, y13 is equal to y. So it's like a symmetrical, as mentioned, it's a symmetrical matrix. Now, this is an example of modeling shunts in the Y bus. Here we have bus I and bus J, and we have the connection to the ground. So, and we have IIJ and IJI and YK in the middle, and YKC over 2 and YKC over 2, which are the admittances connected between the ground and bus A and the ground and bus J. Now, since IIJ is equal to VI minus VJ YK plus VI KC over 2, again, using the Kirchhoff's current law, we have a current coming this way and we have a current coming that way, or we can do it the opposite way. This one coming in is going to be this plus this. Now, this current is this voltage minus this voltage. I'm going to call it I, VI, and VJ over its impedance, which is, or over its impedance or times its admittance, which is going to be YK. And the same thing here, it's going to be VI minus this is 0 volts. So VI minus 0 volts over times its admittance, which is going to be YK. Again, Y is equal to YV. Now, YII is the YII from the other lines plus YK plus YKC over 2. Note that YK is 1 over ZK, its impedance, which is equal to 1 over RK plus JK XK RK minus JXK times RK minus JXK, which is going to be equal to RK minus JXK over R square of K over plus X square of K. Now, if we want to write it in the admittance bus format, we can simplify it. Here, the 2 bus example, the admittances are given, the impedances are given. Z is equal to 0.0 plus J 0.04. Again, Z is 0.03 plus J 0.04, and YC over 2 is J 0.1. Now, what we can do, we can convert that to a bus impedance. First, we want to find the self-admittances, which are going to be, if I divide 1 over this, it gives us the Y, which is going to be 12 minus J15 9 and 12 minus J15 9, which is the admittances that we have that is connected to bus number 1 and bus number 2. Now, let's solve a practice problem for this one. Now, for a 2-bus line, Z is equal to, as mentioned, J 0.04 plus J, I'm sorry, 0.03 plus J 0.04. Now I want to solve this and reach the conclusion that we had in the previous example. So Z, as mentioned, is 0.03 plus J 0.04. Therefore, if I want to find its impedance, Y, it's going to be 1 over 0.03 plus J 0.04. Now to solve this, because I have imaginary numbers in the denominator, I can multiply it by its conjugate. So if I multiply it y times y conjugate, what I get is going to be equal to 0.03 minus J 0.04 divided by 0.03 in a power 2 plus J times J is going to be what? -1. So I get rid of J in the denominator, so it's going to be 0.04 square. Now, 0.04 square plus 0.03 square gives us 0.0025, the denominator. So Y would be equal to 0.03 minus J 0.04 divided by 0.0025, which would be 12 minus J 16. This is one way to solve it. Another way, you can convert it to polar form and then convert it back to different ways to solve. But now I got the admittance. It's going to be 12 minus J 16, same thing that we had before. Now if we include the shunt, Y11 is equal to Y plus YC over 2, which is going to be 12 minus J 16 plus J 0.1 gives us 12 minus J 15.9. And this is our self-admittance. Now the same thing for Y22, it's going to be the same as Y11 because the admittance between them were equal and the admittance that they had to the ground were the same, YC over 2. So therefore, it's going to be again 12 minus J 15.9. Now Y12 is equal to Y21, which is going to be equal to negative Y, which is negative 12 plus J 16. This is the admittance between them, okay? The admittance in the middle. Now, the answer, Y bus, therefore, would be equal to their self-admittance, so 12 minus 15.9J. The admittance between them, so 12 plus J 16. Again, negative 12 plus J 16 here. Off diagonals are the same because it's symmetrical. And then 12 minus 15.9J. Why did we have the same? Again, because these two impedances were, again, the same. If we were different, then you would have a different, diagonal, off diagonal. So this is how we get to this equation. Is it clear? Okay. Now, we can also use the Y bus. If the voltages are known, we can solve it for the current. Now, for that, in that case, Y bus, V is going to be equal to I. In other words, the current injections are known, then we can solve it for the voltages, which is going to be Y inverse times V, which Y inverse is equal to what? Z, impedance. So V is going to be Z bus I, same as what we had for Ohm's law. Now, where Z bus is the bus impedance matrix. So we can have bus admittance matrix and the bus impedance matrix. Now, for the previous example, without converting it to admittance, imagine for the previous example, we had the voltage, which was 1 and 0.8 minus J.2. Then if we have multiplied for them, we could have get the same answer for the current. We could reach the same answer for the current. Now, let's solve this. I'm going to give you again a few minutes to solve this, and I will solve it. Now, using the matrix Y bus and V, we want to find the current injections. So now we have Y bus and we have V. And by the way, I is equal to Y bus V. This is pretty easy, actually. You want me to solve it? Did anyone solve it? No, okay. So if you want to find I1, it's going to be this multiplied by this. Am I correct? Yes. And I2 would be this multiplied by, again, this. Second row in the first. So I1 would be equal to 12 minus J15.9 times 1 plus negative 12 plus J16 times the second term. I can't write it there, so I'm going to write it down. 0.8 minus J.2. Now, if I calculate this, if I compute this, I1 would be equal to 12 minus J15.9. And if I multiply the second ones, it's going to be negative 6.4 plus J 15.8. Again, you can convert it to polar form and then find it, which is going to give us 5.6 minus J 0.1. And in the same way, I2 would be equal to negative 5.58 plus J 0.88. So you can just simply a multiplication, you can find it. Which is the same result that we got here. Oh, this is J 7. Now, solving for the bus voltage, for example, if in the previous case, we assume that we have the current and we didn't have the voltage, then what we can do, we can find the admittance bus inverse, which is the impedance. So we can go back to the impedance, and these are our impedances, and then multiply it by the current so we can get the voltage. And using that, we get a voltage of 0.0738 minus J 0.902 and negative 0.738 minus J 1.098. Now, if we want to find the power, S1 is going to be V1 I1 conjugate, and S2, this is for bus number 1, and bus number 2 is going to be V2 I2 conjugate. We already have the voltage. We can multiply it by a current conjugate, and therefore for the first one, we get 0.37 minus J 4.51, and for the second one, we get 0.35 plus J 5.127. Now, the ones that are negative, you can have it's supplying power, positive, it's actually consuming power. So you can determine the power consumer over their load and the generator as well. Okay, that concludes the power flow model. We will solve more practice problems and continue with that next week. I will post an announcement about your second exam, and also we're going to have a review session next week, and we're going to speak about the second exam as well. Thank you so much, and you have a great day.